Hi, folks. Today we'll have a look at the Reactive Manifesto. So, Reactive Manifesto. Let's see the details as we look into it. Basically, what it argues for is that um software should be written following certain patterns, following certain best practices, and so on. What those best practices, patterns, ways of working, architecting, designing, development should be is present in the manifesto, which we'll review just now, and you can have a look at it on the web at the URL reactivemanifesto.org. All right, so what is it saying? Organizations working in disparate domains are independently discovering patterns for building software that look the same, right? Okay, so independently discovering means that they are reinventing the wheel. There's a hint of that they're finding the best practice independent of each other, whereas good practices, good patterns could be factored out and disseminated across the industry to be followed, right? There's a hint in that. And I believe the publishing of this Reactive Manifesto is a step in that direction by the people that wrote it. Okay. So what does it say? These systems are more robust, more resilient, more flexible, and better positioned to meet modern demands, right? Indeed. These changes are happening because application requirements have changed dramatically in recent years, indeed. Only a few years ago, a large application had tens of servers, seconds of response time, hours of offline maintenance, and gigabytes of data. True, we remember the time not too long ago. For most applications, of course, there were mission critical applications even then, like medical, defense, aeronautics, so on. But as a general commentary on the state of industry, it is true. Today, applications are deployed on everything from mobile devices to cloud-based clusters running thousands of multi-core processors. Indeed, users expect millisecond response times and 100% uptime. That's very true. The expectations of the users are now very high because they have experienced this happening. And they have experienced this happening because the age that we live in uh, enables us things that are available now, mechanisms, hardware, software, knowledge, all of that enables us to make it possible. Hence, the user now have very high bars. They expect a lot from software these days. So a sloppy job does not do it anymore. Data is measured in petabytes. Today's demands are simply not met by yesterday's software architectures. Indeed, we believe that a coherent approach to systems architecture is needed, and we believe that all necessary aspects are already recognized individually. We want systems that are responsive, all right, resilient, elastic, and message driven. So these such systems are defined as reactive systems. So there are details of all of this below. We'll discuss this. All right, so systems built as reactive systems are more flexible, they're loosely coupled, and hence they are scalable. This makes them easier to develop and amenable to change. Change, we all know that it always, happens whether we like it or not. So better to design for it, to architect for change, for extendability, rather than have it come as a shock to us. They are significantly more tolerant of failure. And when failure does occur, it inevitably does sometimes. They meet it with elegance rather than disaster. Reactive systems are highly responsive, giving users effective interactive feedback, right? Okay, so we'll cover these in more detail. So reactive systems are responsive. What exactly is a responsive system? The name gives a hint, but let's see the definition and discuss. The system responds in a timely manner if at all possible. Okay, plain and simple. Responsiveness is the cornerstone of usability and utility. But more than that, responsiveness means that problems may be detected quickly, and dealt with effectively. Okay. Responsive systems focus on providing rapid and consistent response times. Right? Establishing reliable upper bounds, this is important. So they deliver a consistent quality of service. This consistent behavior in turn simplifies error handling, builds end user confidence, and encourages further interaction. Okay, so this is a very loaded definition. Let's break it into parts and study it. All right, so what is it saying really? So what it's saying is, it responds in a timely manner if at all possible. Fair enough. So that timely manner, of course, uh, depends. So this is a non-functional attribute. Timely for one software might not be the same for other. So this is a non-functional requirement. For example, for a medical, software, maybe 1 nanosecond is the time that is timely. Maybe for something else, for a batch processing system, asynchronous batch processing system, uh, doing some, preparation of data during off times, maybe even 1 hour is fine. So of course it depends. But of course, we agree that timely is important. Time, the response time as a non-functional requirement is very important. Okay, so let's move further. Responsiveness is the cornerstone of usability and utility. All right, so what's the difference between usability and utility? So usability is basically the user experience or the UX that a user has when it is using a software. And utility, of course, is the value, right? Utility is the value of the software, whatever that might be. It is the reason someone chooses to use the software. And of course, responsiveness is important, right? If there's a software which is valuable to me, but it does not give me the result in time frame that I want, then I don't value it. Likewise, the more it gives me a good user experience, right? Which is the usability aspect. It's I rather as a user, I would like it to have a good user experience. But between these two, utility clearly is more important, not to say that usability isn't. All right, so in addition to this, responsiveness means that the problems may be detected quickly and dealt with effectively. Okay, so what does it say? Problems are, there are always problems. So if a problem happens, you have to detect it. You cannot not leave it go unnoticed, or you cannot detect it late when its negative consequences have been uh, executed, when it has created havoc. So let's say if your DB has some inconsistency, right? Or your time on the server is incorrect, so on and so forth, an application bug or anything. All of these are things which can happen, right? But the important thing is that the system respond to it and correct itself in time. All right. So what next? So responsive systems focus on providing rapid and consistent response times, establishing reliable upper bounds. This is important. So, there needs to be an upper bound, a ceiling, upper bound. So let's say I guarantee that I have an API, I have a service endpoint, and I guarantee that whoever calls it, request is sent So the response, if I guarantee that, I can provide it within 7 milliseconds. So this 7 millisecond is an upper bound. At times I could provide it in 1 millisecond or 2 or 3. My caller will not bother, he'll be happy. But I have to guarantee that there is an upper bound which I will not cross, right? Hence, this can result in uh, a consistent quality of service, right? And that simplifies other things. Okay, so with that, we move on to the next factor. But before that, let's see how it defines the system, right? So let's see what is a system. So a system provides services to its user or clients, right? Fair enough. That is exactly. So, this is some system. And it provides services. So these three could be, yeah, services. They could be, defined in terms of WSDL, or it could be um, socket call, could be RPC or anything. The idea is that a system exists to provide services, and who calls or uses these services? There is a user of service. Systems can be large or small, in which case they comprise of many or just a few components. All components of a system collaborate to provide these services, right? So if we were to extend this, let's say this system, so in what this box appears externally from a system's perspective, it appears only in terms of the services it defines, but to provide those services, a system has internal components, right, which collaborate with each other as and when needed. Those are components. All right. So in many cases, the components are in a client-server relationship within the same system. Consider, for example, front-end components relying upon back-end components. All right. So this is pretty self-explanatory. A system shares a common resilience model, by which we mean that failure of a component is handled within the system, delegated from one component to the other. It is useful to view groups of components within a system as subsystems if they are isolated from the rest of the system in their function, resources, or failure modes. So this is a bit loaded. Let's break it down. Okay. So what is it saying? So this common resilience model is important. Common way with which it can recover from a system, from a problem, basically. So let's say this outer box is a system. So let's say there is a database within the system. All right. So within this system, you need to have resilience as well, which means you need to have an extra copy of the database, and a common, maybe common API, a common mechanism to deal with this database or a database cluster. So this, having a redundant database or a data copy within the system, guarantees that um, that the system as a whole is also resilient, right? All right. So for example, this is a database, right? And this system, let's say, is it has a front end. Let's say it has a back end, which is some web server. Let's say it's Tomcat web server. hosting some backend application. Um, so for this web server too, there needs to be a redundant a redundant copy of it, so to say. And so that whoever is using this web server within the system, or let's say externally too, knows that, as long as it calls this from behind a certain interface, let's say if it's HTTP. So whether or not an individual web server within a cluster of sorts has failed should be immaterial. As a caller of this subsystem, I should know that resilience has been taken care of, right? All right. It is useful to view groups of components within a system as subsystems if they are isolated from the rest of the system in their function, resources, or failure modes, right? So in this example, the DBMS can be clearly called a subsystem. This web server can be called a subsystem, so on and so forth. And with that, let's go back to the original definition. All right, now we have to see what is resilience. Let's first read it. So the system stays responsive in the face of a failure. This applies not only to highly available mission critical systems, like medical systems, airspace, aerospace, or military avionics or something, they're truly mission critical. Any system that is not resilient will be unresponsive after a failure. It is highly probable that it will indeed be. So resilience is achieved by replication, containment, isolation, and delegation. All right, so these are loaded terms. We'll discuss these. Failures are contained within each component. We saw this a while ago. Isolating components from each other and thereby ensuring that parts of the system can fail and recover without compromising the system as a whole. We just saw this as an example where the DBMS has its own mechanism to recover from failure. Web server has its own mechanism, so on and so forth. Recovery of each component is delegated to another external component, and high availability is ensured by replication where necessary. The client of a component is not burdened with handling its failures. This is the important part. So let's quickly, this is a loaded term, let's quickly, discuss this. So as we saw, let's say this is a system, this is a subsystem, and this subsystem is a DBMS, let's say, which has 3 nodes, 3 or 4, and there is data replication. So the API, whatever that happens to be, of let's say this is a SQL DBMS, SQL based. And so the API, some interface through which you can run queries, is such that the caller should not be bothered by the details, which is to say that even if some node is not available, the caller will typically not even know that such is the case, right? So typically, a cluster is formed, a DBMS cluster, which has a network identifier and a way to call the database services, right? So, but all of that is encapsulated within the cluster. All right. So failures are contained within each component, as you can see in the DBMS side of the system. Any failure is contained within this, right? Let's say if one database node goes down, the cluster takes care of it. Data is redundant, and replication is going on. So the system is still standing. And thereby ensuring that parts of the system can fail and recover without compromising the system as a whole, all right? So recovery of each component is delegated to another external component, and high availability is ensured by replication where necessary. So replication in case of data, you have to replicate things whenever there is state involved, right? So if there is state within the system, then to be redundant, you have to replicate that state basically. And it says that recovery of each component is delegated to another external component. Well, depends. Sometimes the cluster internally can, um, you know, can self-heal, if possible. Maybe this is a separate VM, or it can be restarted, diagnostics can be run, auto healing can be performed. Or let's say when this goes down, some kind of an observability node is notified, an external observability node, that a system has gone down, and this observability node carries out remedies, right? Okay, so with that we move on and go back to the top of the definition again. All right, so let's see how is failure defined. All right, a failure is an unexpected event within a service that prevents it from continuing to function normally. Okay, see, it is defined differently. It is not, it is that you have to pay attention to the fact that an error is different from failure, right? So we'll look into it. All right. Okay. A failure will generally prevent responses to the current and possibly all following client requests. So an error, if it happens, can be recovered from. And if it can be recovered from, that means that it has already been anticipated in the current context. You can only recover from it if you expected that such a thing could have happened, right? Failure is different. So failure is, remember this part, it's an unexpected event, right? Okay. Hence, it generally prevents responses. Let's see further. This is in contrast with an error, which is an expected and coded for condition, right? So as I mentioned, error is anticipated, right? If you have coded for it, that means you have already anticipated it, right? So you can anticipate errors and, define what to do when an error occurs. For example, this is what we do in exception handling, in object-oriented, or in checking API return codes, so on and so forth. Etc. For example, an error discovered during input validation that will be communicated to the client as part of normal processing of the message. This is a good example. If you have a form and the user inputs, let's say alphabetical characters in a text box where you only expect numeric, when you anticipate for it, you will have a regular expression which checks. You'll see, okay, there's some fault. You'll tell the user, hey, only input text over here. All right. Okay. Failures are unexpected. So the key thing is a failure is unanticipated, basically, and will require intervention before the system can resume at the same level of operation. Okay, this does not mean that failures are always fatal. A truly reactive system, in a truly reactive system, the failures, even the unexpected, unanticipated errors will not have the system collapse, right? That is how to do that. Of course, there are ways. This does not mean that failures are always fatal, rather that some capacity of the system will be reduced following the failure. So there are many ways to recover from such a failure. Of course, redundancy is one way. If a subsystem X fails, you can have an entirely redundant subsystem that is a copy of it in terms of capacity, in terms of state, in terms of availability and all other requirements. And without the client even noticing, it can take over. So even though a subsystem has failed, a redundant subsystem can resume the services of its peer, right? Okay. Errors are an expected part of normal operations, are dealt with immediately, and the system will continue to operate at the same capacity following an error. So we'll discuss some examples as well. Examples of failures are hardware malfunction, it happens, processes terminating due to fatal resource exhaustion. Of course, uh, that would typically be a software bug or a defect in architecture or design or inability to anticipate something. Program defects that result in corrupted internal state. So these are some examples of failures. So let's cover, let's discuss some examples, something. All right. So let's say we have a system. All right. There's a system. So let's say it has two parts, and let's say for the sake of discussion, there are two database nodes, DB node 1, DB node 2, and the data is replicated between them. So let's say we have a software over here. It writes into DB1, and there is some other part of software S2 here. It is only used for reading, it only reads from DB2. Or let's say both of these are part of a cluster and they have the same network address. Let's say over here, this is the address. This software one, it has to make write request over here. This software two, it makes read request over here. So this could be something like a proxy or a cluster or whatever, but you know, get the idea. So let's say currently this cluster behaves in the manner, is configured as in a manner whereby all the requests are evenly distributed in a round robin fashion, right? Let's say if 100 requests per second are coming into this cluster. Let's say there is some internal cluster manager here which ensures that on the average 50 of them go to DB1, 50 of them go to DB2, right? So this is evenly distributed and round robin. All right. Let's say for the sake of discussion that there is now let's differentiate between error and failure. So let's say, what would an error be? So let's say just a trivial example, if we try to insert into some table a row where, you know, data does not match the schema, right? Not per schema. So this is an error. This will throw up an error and the application software will deal with it, right? A failure is, let's say this entire DB2 node gets down. Maybe there is a hardware malfunction. Maybe the RAM got messed up. Maybe the processor got fired or whatever. So if this happens, remember all the time this cluster is replicating state internally. What will happen? From the external point of view, the database is still there, right? Both of these software will keep working. Database writes will keep on happening. Database reads will keep on happening. However, on the average, if you remember, we said that 100 requests per second on the average were coming into this database cluster, and 50 were handled by DB1 and 50 by DB2. How exactly? Some internal load balancer within the DB cluster was doing this, right? That was doing this. All right. This was opaque to the application software. So what happens now is that with this node being down, all of these 100 requests, this load will be borne by the DB1. So till the time someone is notified and corrects and brings on a further database instance, this instance will bear the additional load as well, but the system will still remain functional in the face of failure. All right. So even though we did not anticipate that the hardware, the processor or the RAM or whatever of this database instance will go down at time XYZ, whatever, but we could still recover from failure because we had a cluster of database, right? So I hope this makes it somewhat understandable. Let's go back. We were discussing resilience. I think this is taking a little bit of extra time. So we'll carry on from this point in a subsequent lecture. Take care, everyone. Have a good day.